Alright, ladies and gentlemen, class recording has started. So, as I mentioned to you guys earlier, the next section of chapter 5 deals a lot with applications of things that we talked about in the previous section. Things like force and net force and acceleration and mass and inertia and Newton's second law, how all these things are related. The first part of section 5.2 deals with gravity. We've talked about gravity on several occasions up until now. We talked about the acceleration of gravity, right, being constant. And the first thing we did was we talked about it just dropping this object, right, using the acceleration of gravity in a kinematic equation to find how long it takes the ball to hit the ground, blah, 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 blah. Then in the last chapter, we talked about, well, actually before that, we talked about that gravity doesn't only affect things going straight down, but it also affects things up and down, right? That it causes an acceleration the entire time. And then last chapter, we talked about how gravity affects things in 2 dimensions, right? That it only affects the vertical motion, but not the horizontal motion. I've been careful up until this point to make sure that when I discuss it, I was talking about it in terms of how gravity affects that object, or gravity is the only thing affecting that object, because we haven't really introduced terms yet. But now that we know it, right, we can talk about that gravity is actually a force. Gravity exerts a force on objects, and because of that, it causes acceleration. The force that is exerted by gravity, we give a special name, we call it the weight of an object. So the weight of an object is just the force that gravity is acting on that object. In terms of how big of a force does gravity exert on that object, we go back to Newton's second law. Here's Newton's second law, not written in the form that we introduced it earlier, right? We introduced it as F equals ma, but if you divide both sides by m, you just rearrange the equation and you get this. A couple chapters ago, we found out that acceleration, the acceleration caused by gravity, we give a special letter, right? We call it lowercase letter g. And that was representing the acceleration caused by gravity, which here on Earth we know is 9.81 meters per second squared. If we plug that into the equation for acceleration, because that we know that's the acceleration that gravity causes, and then for the F in that equation, we just substitute in the W for weight, we can rearrange this equation and get this. Okay? This is how we calculate the force that gravity is acting on an object. We take that object's mass and multiply it by the acceleration due to gravity. So the weight of an object is equal to m times g. Its mass times the acceleration of gravity.
Mass in kilograms, right?
Yeah. And then here, because this is a force, right, that unit will be in newtons. So now it's just said that newtons, remember, newtons involves, is a derived unit that includes kilograms, right? So in this case here, we have to make sure that this mass should be in kilograms. And that will give us the force that gravity is acting on that object. Good there? Now, before we get into applying that, one thing that we take a look at, mass and weight, 2 terms that up until now you've probably used pretty much interchangeably, right? That they kind of mean the same thing. But we find out here that they are not the same thing. They represent 2 different things. We just discussed that weight is a gravitational force that is measured in newtons. So weight is a force. It causes acceleration. But the mass of that object, mass is a measure of the inertia of an object and is measured in kilograms. So we've talked about inertia in the previous section. We said inertia is that tendency for an object to do whatever it is currently doing. If it's sitting still, it will remain sitting still. If it's moving, it will continue moving, but in a straight line. Things that are heavy have a lot of inertia. They are hard to get them to start moving. That's why it's hard to push heavy things. But they are also harder to stop, right? However, how hard or easy it is to start or stop something does not depend on the location of that object. But weight, defined as the gravitational force, does depend on location. For instance, if we look down here at the bottom, if we want to calculate the weight of something here on Earth, we just learned up here at the top, right, that we take the mass of that object and then we multiply it by the acceleration of that object here on Earth. So here's the mass, right, 81 kilograms, and then this is the acceleration of gravity here on Earth. And that would give us a weight of 795 newtons, because it's a force, right? Keep in mind, the weight that you're most familiar with, like in pounds is a unit of force in like English units, right? Like feet and things like that, okay? So even when we talk about your weight being, whatever, 120 pounds, that's still a force. But if we talk about the weight of an object, if we go somewhere else, like on the moon, we still take its mass and we multiply it by the acceleration of gravity. Mass doesn't change. It's still, that whatever the object is, the person in this case, still has a mass of 81 kilograms. But the acceleration of gravity on the moon is different. So therefore, the weight of that object will be different. Not because it's a different object, but because the effect of gravity is different on Earth than it is here on the moon. So weight, being a gravitational force, depends on how much gravity are we talking about. But mass, being just the amount of material that makes up an object or its inertia, doesn't depend on where we're located. Okay? Margo, question, or are you good?
So do you do someone's weight in newtons?
You can measure somebody's weight in newtons.
Yeah.
That's not the unit that we generally think of it in. We think of it in pounds because we're not, we're not with the rest of the world because we're America, we don't need to follow
They
rules.
do it in newtons? How is it in kilograms?
Usually, when you talk about something's weight,
Yeah.
like in Europe or somewhere else, they generally talk about it in terms of kilograms. So they're not actually describing the weight of that object, they're actually describing the mass of that object.
Okay.
Here on Earth, that really doesn't make a big difference because we all have this same acceleration of gravity.
So what, like in NASA, would they do like newtons?
They would probably go newtons, yeah. They'd probably go newtons as far as like force and things like that. Okay. All right. Good there? Okay. Let's start applying this. All right. It's down there at the bottom of the page. There is a situation that you may or may not be familiar with. Okay. So it says, your groceries are in a bag with paper handles. It says the handles will tear off if a force greater than 51.5 newtons is applied to them. What is the greatest mass of groceries that can be lifted safely with this bag in two situations? We're going to look at part B first, where it says we're going to lift this bag with an upward acceleration of 1.25 meters per second squared. So that would be like you taking this bag, putting it full of groceries, and then lifting it off the counter to carry it to your car, right? What's the most amount of groceries that we can put in that bag without the bag tearing? Okay? First, what is this question asking us for?
Weight, mass.
It asks us for mass, right? So what is the greatest mass of groceries? So our unknown in this problem is mass. Okay? All right. Some things that they told us. What did they tell us about this situation? Go ahead.
51.5 newtons.
Okay, so this is a 51.5 Newton force is applied. that's how hard we're going to pull on that bag, okay? And remember last week, we talked about the idea that we'll represent force with the capital F and then a subscript, and we talked about that if you're pushing or pulling something, a lot of times we'll call that F of A for the applied force. So in this case, the applied force is 51.5 newtons, okay? That's how hard we're pulling on this grocery bag. What else does it tell us about the grocery bag?
It's acceleration.
It's accelerating, right? Upward acceleration of 1.25 meters per second squared. So in this case here, the bag experiences an acceleration of 1.25 meters per second squared. Okay?
What's the A with the F?
That is, say, the F stands for force, right? A lot of times we'll use the lowercase a to represent an applied force. So that's just you pushing or pulling or whatever.
What
Okay.
would be an example of another?
Like if we do like a frictional force, sometimes we'll use like F of F, you know.
Yeah.
So, and then we'll see that there's one that's kind of important that we need in this problem. But we always represent forces with F, and then we use the subscript to sort of just distinguish them from one another.
Okay.
All right. First step in doing these problems, we got to analyze the forces, and we got to analyze all of the forces. So it is generally beneficial to us if we start with a free body diagram. Okay? A free body diagram is a picture that shows our object and all the forces that are acting on that object. So there's my grocery bag, and there's my handles. Okay? All right. Forces that are acting on my grocery bag. We've already talked about one, right? What force do we need to draw on here first?
Acceleration.
Acceleration
Or
is a
gravity.
force. Let's start with this one that we already labeled here. Okay? So we know that we're going to apply a force to this grocery bag. Okay? If we're going to get the grocery bag to go upward, which way do we have to apply the force? Probably upward, right? So I'm going to take this and I'm going to draw an arrow that starts from the middle of my grocery bag and goes up in this direction. Okay? And I'm going to label that force F of A for the applied force. And I know how big that force needs to be, right? 51.5 newtons. Okay. But we talked about in the previous section that if we really want to analyze the motion of this object, we have to look at all of the forces, right? Or the combined effect of all the forces. Is this the only force that's acting on that grocery bag? It's the only force that we're putting on that grocery bag, but if we're lifting something upward, we have to deal with what? Gravity. Okay? Gravity acts which way? Down. Right? So we're going to draw another arrow on here that's acting downward. Now, a couple of things. First, we just learned that in the previous slide that we call the force of gravity acting on something what? What do we call the force of gravity acting on something?
Weight.
It's weight. So a lot of times you will see it labeled W for weight. Okay? I am not a big fan of this notation, and here's why. This is a force. It does, or it can do, exactly the same thing as every other force that we may act on it. It's not any different than this force of us pulling, or the force of us sliding, or friction acting on it, or anything else. So I don't like the fact that we write it some way different. So generally, the way I do it is I will label this as F, just like every other force, but then I will use the lowercase subscript G to represent the force of gravity. Okay? Not that it is beneficial, not that it is essential to solving this problem, but how big is this gravitational force going to be compared to my applied force? Bigger or smaller? Smaller. Why? Which way is the bag accelerating?
Upward.
Upward. So if we're going to have an upward acceleration, our upward force has to be bigger than our downward force. Not that you need to draw it that way, but, you know, to get in the habit of doing it might be a good idea. We just learned that the force of gravity depends on two things. It depends on the mass of the object, and then the acceleration of gravity at that location. The force of gravity is equal to m times g, the mass of this grocery bag, times g, the acceleration of gravity. But we have a problem here, right? What's the problem?
We don't know them.
We don't know the mass of this grocery bag. That's what we're trying to find out. So we can't go much further than this, but we do know that the acceleration of gravity is 9.81, so we can simplify this just a little bit by calling it this. Okay? We don't know the exact number yet, but we do know that it's going to be 9.81 times whatever that mass is. Good so far? When we analyze an accelerating object, Newton's second law tells us the relationship between net force, mass, and acceleration. On the left-hand side, net force, we said, what does the sigma represent? What does the sigma tell us to do? Total, the sum, right? There are two forces that are acting on this grocery bag. F of A plus F of G. The sum of those two forces is equal to m times A. Okay? Good there? Then we start filling in things we know. We know that the applied force is 51.5 newtons plus, we don't know the actual force of gravity, but we do know that it's going to be 9.81 times whatever the mass is, equals the mass, which we don't know, times the acceleration, which is 1.25. Good with where that all came from. Before we go any further, though, we have to take care of the fact that these forces are vectors, right? And because they're vectors, they have to have both magnitude and direction. Applied force is upward, gravity force is downward. How do we distinguish between those two? How do we tell that one's up and one's down? Make one negative and one positive, right? Generally, although you don't have to do it this way, generally, we're going to call up things positive and down things negative. It just kind of makes the most sense. So really, this force here is not 51.5. It's actually positive 51.5. And this gravitational force is not 9.81 m. It's negative 9.81 m. And then the plus and minus applies to any vector quantity, anything that has direction. What did it tell you about this acceleration of the grocery bag? Upward, meaning that it should have what sign? Positive. Anything upward is going to be positive. So now, it's just a matter of simplifying this up a little bit, right? Right, and m shows up twice in this equation, but nothing I don't think we can handle, right? And when you plug that all in, you find out mass, I think it should come out as 4.66. So that's how much mass we can put into that grocery bag so we can lift it without it actually breaking. Good there? Barbara, go ahead.
How'd you get 4.66?
So these are two m's, right? This is m and this is m, right?
Oh, okay, never mind.
So we got to get the m's together, so
Yeah.
add that to both sides.
Yeah, I
Did you see that?
Yeah, I didn't have it as M, so I just, like,
Okay, yeah.
I got like 33.
Because remember we said we don't exactly know what this force of gravity is, but we do know that it has M in it. So we have two M's in that equation, but we can add them together and bring them together and stuff like that. All right, good there? Okay. Another example similar to that is on the top of the next page. Let's talk about this firefighter as he slides down this pole. Okay. So it says, fire alarm goes off and a 97-kilogram firefighter slides down a pole with a constant acceleration of 4.2 meters per second squared. What is the upward force exerted by the pole on the firefighter? So, the fact that he has an acceleration of 4.2 meters per second squared is going to tell you that there has to be something else besides gravity, right? If gravity was the only thing acting on him, what would his acceleration be as he slid down the pole?
Negative 9.81.
Negative 9.81, but it's not. And so, in this problem here, right, what is the upward force? Okay, so we're looking for a force. Generally, what force is that probably going to be?
Positive?
Well, it's going to be positive because it's upward, right? What should we call it? What's that force that acts in the opposite direction of the way things are moving?
Friction.
It's a frictional force, okay? We'll learn more about friction a little bit later on in this chapter, but right, we're looking for a frictional force, okay? Things that we know. 97 kilograms. That's the mass of the firefighter. And then it tells us sliding down the pole with a constant acceleration of 4.2 meters per second squared. So it gives us the acceleration 4.2 meters per second squared. Okay? Good with that?
Yeah.
All right. Here on the right, they gave us a picture. Okay, I'm going to dress this picture up a little bit better. Okay, so forces. Can't get rid of gravity. It's always there, right? And as you can see in the picture, it's labeled as W, okay? Or we can label it as F of G. And we learned earlier that to calculate the force of gravity, we take the mass of the object and multiply it by 9.81, the acceleration of gravity in that location. It told us that this firefighter has a mass of 97 kilograms. We know that the acceleration of gravity here on Earth is 9.81. So in this case, we can figure out how big that gravitational force is going to be. Mark, go ahead.
Why don't we make it negative?
Hold on 1 second to that question. Okay? $9.52 if we round it. All right. Walker, we talked about the idea that there is another. Sorry. Walker, what does the negative on the force tell you?
Oh, direction?
Direction. Can you tell what direction that force is going in from this picture?
Yeah.
Yeah, because why?
It's going down.
Because there's an arrow, right? Okay. So in this picture, it's not really critical that we make it negative, all right? Because the negative is telling us the direction. But now, if you make it negative, that's fine.
Will it mess up our calculation though?
No, but it is important when we put that number in a calculation.
Okay.
Because here, I can tell the difference between this force and this force in the picture, right? I can tell the difference in direction because I can see it. But when you put it in an equation, now it's not quite as obvious. That's where the positive and negative really becomes important. Okay? So here, we've already said that there's another force here in the upward direction, and we've kind of assumed that that's going to be a frictional force, but we don't know what that one is right now. Okay? So, an accelerating object, we analyze using Newton's second equation. Sigma F means net force, right, or the total force. Again, there are two forces here, F of F plus F of G, because we got to look at the combined effect of all those forces. Those together equal M times A. Good there? All right, we don't know what F of F is, so we'll keep that just as an unknown. Plus, we just calculated that that force of gravity is 952, and that equals the mass, which they told us was 97 kilograms, times the acceleration, which was 4.2. Okay? Now, before we start going and doing this real quick, right? Now it's important that we add those signs, right? So 952, what sign is that going to have?
Should be negative.
That's going to be negative, it goes down, right? But, what does it tell you about the acceleration in this problem?
It's negative also.
Because it's sliding down, right? Sliding down the firefighter pole. So anything down has to be negative, okay? Now, does that mean that the firefighter is slowing down because he has negative acceleration? No, it just means what? Downward direction, right? So now, it's just a matter of going through and solving for F of F. For the frictional force that is acting on the firefighter.
Quit laughing.
Rounded it would be 5.
Yeah, I guess you could round it. Well, really, we probably should round it to 2 sig digs, so we could round it like that. But that's details. And again, just to make sure we're consistent, right? This came out as a positive number. Should it come out as a positive number?
Yes.
Because it's pointing which way in our picture?
Oh.
Up. Also, how big is it compared to the gravitational force?
Smaller.
Smaller, right? And that's good because which way is the acceleration occurring?
Down.
Downward. So we should have a bigger downward force than upward force.
Yes.
All right, good there?
Yes.
Okay. One last thing before we take off here. Okay. This book, as it sits here on the counter, or this can of soup that's sitting here on the kitchen counter in the picture, okay? If we look at them, how would we describe the acceleration of that object? What's the acceleration of the book?
Constant.
More specifically, it would be 0, right? 0 acceleration also means there needs to be 0 what? Not necessarily true. 0 acceleration doesn't necessarily mean 0 velocity.
Oh, zero forces? Like,
It has to be, so that means that the what
net
has,
forces have to be.
the net force has to be 0. Okay? Is gravity the only force acting on this book as it sits here on the counter?
No.
No. If it was, what would it do? It would fall downward. But it's not, right? Why? What's preventing it from falling downward? The counter, right? The counter applies what we call a normal force to that object. Okay? The normal force is always perpendicular to a surface. In this case, the table provides the normal force. In your case, your chair provides a normal force. If your chair wasn't pushing up on you, what would happen to you? You'd fall downward under the influence of gravity. Okay? A lot of times, normal force is equal to the gravity that is acting on an object, but not always. Alright? We will look at that in a little bit more detail tomorrow when we do this section right through here. Okay? So we'll do this problem tomorrow, and then we'll get into the idea of apparent weight and equilibrium.